As an example of the second case of time-dependent perturbation, let's now consider the interaction of a harmonic field with an unperturbed system, or say an atom having a Hamiltonian, say H0. And this is clearly a case of harmonic perturbation. In harmonic perturbation, the perturbation or the perturbed part of Hamiltonian or the time-dependent perturbation is a harmonic variation in time and can be conveniently taken as, say, H prime of R, the space-only dependent part of the perturbed part of Hamiltonian or perturbation, into cosine of omega t. Clearly, cosine of omega t is a harmonic variation. To rewrite this in a convenient manner, I'll put a constant part also, and this constant happens to be, say, 2, so that I can have a substitution for 2 cos omega t, where omega is the frequency of the perturbation itself. So we will rewrite 2 cos omega t as e raised to I omega t plus e raised to minus I omega t, so that we conveniently write the harmonic perturbation term as h prime of r, which is constant in time, into e raised to I omega t plus e raised to minus I omega t. And this situation is similar to a harmonic wave, as in the case of electromagnetic radiation interacting with matter, or a harmonic wave or a harmonic energy interacting with matter. Now the probability amplitude, or the general expression for probability amplitude, ck1 of t becomes ck1 of t equal to 1 by IH cross integral from 0 to t h prime kn of r comma t prime e raised to I omega kn t prime dt prime, where omega kn is the frequency difference between the initial and final quantum states, connected by means of a transition governed by this harmonic perturbation. Here h prime kn, that is scalar product k, h prime n is scalar product k, h prime is h prime of r e raised to I omega t plus e raised to minus I omega t ket n. Now we take this time dependent term out of the operator, as this state vector has space only dependent part. The time dependence we have already taken out here, e raised to I omega kn into t prime, so that these terms that are underlined are space only dependent terms. So the time dependent term is homogeneous and is taken out. Scalar product k h prime n remains in this scalar product, e raised to I omega t plus e raised to I omega minus I omega t is taken out. Then ck becomes h prime kn. This is now clearly h prime kn by IH cross is taken out, because these are the terms that are either constants or are constants in time. Integral 0 to t e raised to I omega t prime plus e raised to minus I omega t prime. Here also I'll have to account for this t prime, that is the variable for integration, as t is a definite integral, definite limit of integration. E raised to I omega t prime plus e raised to minus I omega t prime into e raised to I omega kn, or e raised to I omega fi, final initial states t prime dt prime. Now we open this bracket. The terms out of this integration are retained. Integral 0 to t, this one into this one, make it e raised to I omega kn plus omega t prime, plus this one into this one, make it, say, e raised to I common omega kn minus omega into t prime dt prime. Now we integrate this e raised to I omega kn plus omega t prime dt prime. Integral of exponent is exponent itself divided by I omega kn plus omega. In the limit 0 to t, this becomes e raised to I into omega kn plus omega into t minus upper lower limit 0, make it, say, e raised to 0, which is 1, divided by omega kn plus omega. And the second term upon integration and after applying the limits becomes e raised to I into omega kn minus omega into t minus 1 divided by omega kn minus omega. Now this corresponds to the probability amplitude for two different terms because there is a summation. Yeah, this constants on the outside this bracket are also applicable for this term also. So we'll have to look into the physical meaning of these two situations. The first term will have a maximum value when the denominator tends to 0, and the second term will have a maximum value when the denominator of the second term omega kn minus omega tends to 0. So consider the first term. This will be maximum when omega kn plus omega equal to 0. Multiply this by h cross, then this becomes h cross omega kn is omega k minus omega n. So h cross omega kn is h cross omega k minus h cross omega n plus h cross omega, that's equal to 0. H cross omega k is the energy of the kth quantum state or final quantum state EF, equal to, you take this term to the right side and the remaining two terms to the right side, minus h cross omega n becomes h cross omega n upon, say, sending to the right side, that is h cross omega n, which is the energy of the initial quantum state, minus h cross omega, that is the energy supplied or absorbed by the harmonic perturbing term or the agency that is reasonable for this perturbation. So energy of the final state is equal to energy of the initial state minus a definite amount of energy, or say we will say it's a quantum of energy supplied by the agency applying the perturbation. So during this process there occur a reduction in energy for the system because energy of the system is lowered by a definite amount equal to h cross omega. That means energy of the final quantum state is energy of the initial quantum state minus a definite quantity. That means again energy of the final quantum state is less than the energy of the initial quantum state. Then this activity has only one possibility. The system is already occupying some of the higher energy states permitted to it. When it undergo an interaction with this harmonic perturbation, then it will be supplying energy to the agency reasonable for perturbation and undergo a de-excitation to its one of its lower energy state permissible to it. Definitely this process is associated with the loss of energy, of course in the form of photon, to the external agency reasonable for this kind of an activity. That means you have an incoming photon having an energy h cross omega coming to make an interaction with this system consisting of an electron occupying some of its higher energy state. In the presence of this incoming photon, the electron undergo a de-excitation so that the energy of the final state is lesser than the energy of the initial state. Along with this process, it will emit a photon having an energy equal to the difference in energy between the initial and final quantum state. So that during this process, by supplying one photon, you will be able to get two photons having the same energy, say h cross omega. Of course, there are some limitations for this process. The energy of the incoming wave or photon or the incoming harmonic perturbation should be equal to the difference in energy between these two quantum states connected by means of this transition. However, during this process, by supplying one photon, you are able to get double the photon having the same energy. This accounts for a light amplification, and this process is referred to as stimulated emission, which forms the working principle of light amplification by stimulated emission of radiation, or say the so-called laser. And this process is referred to as stimulated emission. So when omega kn plus omega is tending to 0, the probability for stimulated emission will be maximum. And similarly, once you consider this one, omega kn minus omega equal to 0, that means h cross omega k minus h cross omega n minus h cross omega equal to 0. That means h cross omega k equal to h cross omega n plus h cross omega, or energy of the final quantum state equal to energy of the initial quantum state plus h cross omega. So during this process, electron occupying some of its lower energy states absorb energy from the incoming harmonic perturbing agency and get promoted itself to some of its higher energy state, having energy difference equal to the energy difference equal to the energy supplied by the incoming perturbation agency. So the process is like this. You have an electron occupying one of its lower energy state. Now you have a harmonic perturbation or a photon having energy equal to say h cross omega coming, that undergo an interaction with this electron so that the electron absorb an amount of energy h cross omega from this agency of perturbation. So this photon will be lost and electron get excited to an energy state, say EF, equal to having energy equal to the energy of the initial state plus energy absorbed from the photon h cross omega. So this is clearly an absorption of photon from the incident beam and hence is referred to as induced absorption. So during the interaction of a material medium with a harmonic perturbation, there are scope for two different processes. One, induced absorption, and the second one, stimulated emission. Here also we will prove that the mathematical transition probability for stimulated emission and induced absorption are equal. This is further referred to as the principle of detailed balance, but here also we have this argument that generally the population in the lower energy state will be largely exceeding or exponentially exceeding the population of atoms in the higher energy state, since there are more atoms that have scope for absorption rather than the population of atoms that have scope for emission. Generally, the intensity or the transition probability for induced absorption will be much larger than that for stimulated emission. But mathematically these are exactly identical, and this concept is referred to as the principle of detailed balance, as we have seen in constant perturbation. So either you can consider the transition probability for stimulated emission or that for induced absorption. The mathematics are exactly alike. We will do the transition probability for induced absorption. So the transition probability amplitude is I omega kn minus omega is there. I into IH cross make it say minus 1 minus h prime kn by h cross e raised to I omega kn minus omega into t minus 1 divided by omega kn minus omega. Here for one step I have made this arrangement theta equal to omega kn minus omega into t. So h prime kn with a minus sign divided by h cross e raised to I theta minus 1 by omega kn minus omega. Now let me take e raised to I theta by 2 as a common factor from this term e raised to I theta and 1. h prime kn by minus h cross is retained, e raised to I theta by 2 is taken out into e raised to I theta by 2. Once you multiply it, e raised to I theta by 2 plus I theta by 2, make it say e raised to I theta. Minus, in order that you make it 1, this should be e raised to minus I theta by 2. Now we replace theta by means of omega kn minus omega into t. So this is minus h prime kn by h cross e raised to I into omega kn minus omega into t by 2 by omega kn minus omega into this one e raised to I theta by 2 minus e raised to minus I theta by 2, that is 2I sin theta by 2. Instead of theta we have omega kn minus omega into t. So this term is written here into the quantity in this bracket is 2I sin of theta by 2. Theta is omega kn minus omega into t divided by 2. So 2I is taken to the constant regime minus 2I h prime kn by h cross e raised to I into omega kn minus omega into t by 2 by omega kn minus omega into sin of omega kn minus omega into t divided by 2. So the probability of transition from an initial state n to a final quantum state k is square of this one, that is minus square, this is a complex function, so the square will be square of negative, make it positive, complex conjugate of this one minus I into the function itself I, make it say minus I square, which is plus 1, 2 square 4 h prime kn square, h prime kn complex conjugate into h prime kn by h cross square into e raised to minus I omega kn minus omega into t by 2 into e raised to I omega kn minus omega into t by 2, make it 1 divided by omega kn minus omega whole square is written here, square of sine term, that is sine square of omega kn minus omega into t by 2. Now this probability for transition is exactly identical with the probability of transition that we have met in the case of constant perturbation, with the only difference being the omega fi term in constant perturbation is replaced by means of omega kn minus omega in this case of harmonic perturbation. Here also we make the analysis of this transition probability for induced absorption under harmonic perturbation. That could be done by analyzing the variation of this probability with time as well as the energy difference between the initial and final quantum state. Here also with time this probability follow a sinusoidal variation, with the maximum probability being for h prime kn square by h cross square into t square divided by 4 for h prime kn square by h cross square into omega kn minus omega whole square, this one, and this is a sinusoidal oscillation. The arguments that we have, the inferences that we have made in the case of constant perturbation can be made here also. The transition probability undergo a sinusoidal variation with time. As time increases, this increases to reach a maximum value for h prime kn square by h cross square omega kn minus omega whole square. When time becomes, say, t becomes 2 pi by omega kn, pi by omega kn minus omega, this will be maximum, and when time becomes an even multiple of 2 pi by omega kn minus omega, the probability will be minimum. So that is the second inference. When time t equal to 2 pi by omega kn minus omega, the probability for transition is maximum, and this maximum value of probability is for h prime kn square by h cross square into omega kn minus omega whole square. When the time of exposure is an even multiple of 2 pi by omega kn minus omega, when t equal to 2 pi by omega kn minus omega, this becomes omega kn minus omega vanishes, 2 pi by 2 make it say pi, sin pi is 0. So the probability amplitude will be 0. And finally the probability oscillate between a maximum value for h prime kn square by h cross square omega kn minus omega whole square and 0. Now the variation with the energy difference or omega kn minus omega, or say omega kn minus omega, omega kn minus omega. Here also for no transition the probability is maximum, and this maximum value is h prime kn square t square by h cross square. As the energy difference increases, this probability will be falling, so that there is greater transition probability between adjacent quantum states. When the energy difference is equal to 2 pi by t, this transition probability is 0, and it is 0 for any even multiple of 2 pi by t also. So you cannot account for a greater transition by increasing the exposure time, and you can expect transition between adjacent quantum states having greater transition probability comparing with the transition probability between two quantum states that are placed far away. And further, mathematically, the transition probability for corresponding to an excitation transition is exactly equal to the transition probability corresponding to a de-excitation transition, or the principle of detailed balance is valid in the case of harmonic perturbation as well. Now, we have seen the two possible cases of perturbation. Now we will have to apply these results to a practical situation. Generally, quantum states are assumed to be part of a continuum rather than they are being treated as a part or as some say discrete energy states. Then in a practical point of view, rather than evaluating the transition probability between discrete quantum states, we will be interested in evaluating the transition probability between or from an initial discrete energy state to a final continuum states rather than a discrete state. And this gives us a very important result in time-dependent perturbation theory, which has applications in describing any situations that involve the application of time-dependent perturbation theory. The immediate applications include the evaluation of scattering cross-section in Born approximation, or the so-called Fermi theory of beta decay that you, I think, might have already discussed in nuclear physics. This is the derivation of Fermi's golden rule that include the evaluation of the transition to continuum state. So transition probability in both constant perturbation and in harmonic perturbation, we have seen that transition probability is maximum among adjacent states, and this is found to be directly proportional to time. So you look at this curve, the total transition probability will be equal to the area under this curve, or this is true in the case of constant perturbation as well. The total possible transition accounted by a perturbation will be equal to the area under this curve, and majority of this area is contributed by means of this bell-shaped curve between the first two secondary minimas. And this curve will have an area that is proportional to the product of this length and this breadth. This length is equal to, or this height is proportional to t square, and this breadth is proportional to 1 by t. From minus 2 pi by t to 2 pi by t, this breadth is 4 pi by t. So this is proportional to 1 by t. So that this area will be proportional to t square into 1 by t, that is proportional to t. So the total probability for transition will be proportional to t. If that is the case, then the transition per unit time will be independent of time. Since the total probability for transition is directly proportional to time, to evaluate the rate of transition, that is the transition per unit time, you will have to divide this by means of t, time, so that this will be constant in time. It is this result that we will have to prove mathematically as long as transition to continuum is concerned. Further, rather than considering discrete final state, we will be assuming continuum final state. Final state will have some continuum distribution of energy around an expected discrete state. So rather than considering a one-to-one transition, we can consider one to many quantum states transitions. These quantum states are assumed to be part of a continuum. So this is why we require to have a probability for transition to be evaluated to a continuum rather than a discrete state. So rather than a discrete state from n to k, one-to-one transition, practically we will have quantum states that are part of a continuum. In constant perturbation, we have seen that the probability of transition is for h prime square by h cross square omega square sin square omega t by 2. In harmonic perturbation, we have done it in the case of induced absorption. If you are interested, you can evaluate this for stimulated emission as well. In such a case, you will have to replace this minus sign by means of plus sign. The total transition probability is found to be for h prime kn square by h cross square sin square omega kn minus omega t by 2 divided by omega kn minus omega whole square. So the only difference being, here you have omega, here in this case that is to be replaced by means of omega kn minus omega. Let the density of states around the final quantum state Ek be rho of Ek. For you have, or we assume that we have continuum quantum state in the range from Ek to Ek plus dEk. Let the density of states, that is the number of quantum states. This is purely a statistical evaluation. This I think you might have done in statistics several times. In this regime, let's assume that there are rho number of quantum states per unit energy difference. Then the total number of quantum states between Ek and Ek plus dEk will be equal to density of states into the energy difference dEk. Then the probability of transition to dEk will be equal to probability of transition into the number of quantum states in this regime, because we have evaluated this probability of transition to a single quantum state. Now we assume that there are rho of Ek into dEk number of quantum states. Then the probability of transition to this continuum will be equal to probability of transition to this simple discrete energy state into number of quantum state in this regime. Then the overall probability of transition to continuum range dEk can be evaluated by integrating this probability of transition over an infinitesimal range of energy dEk over minus infinity to plus infinity. So this overall probability of transition equal to integral minus infinity to infinity for h prime kn square by h cross square sin square omega t by 2 by omega square into rho of Ek dEk. Now this is to be integrated. When t is very large, with the main peak become very small, so that h prime kn and rho of Ek can be taken as constants. Then P becomes 4h prime kn square by h cross square rho of Ek integral from minus infinity to infinity sin square omega kn into t by 2 by omega kn square dEk. Now we make a substitution, x equal to omega t by 2 that is Ek minus En by h cross into T by 2, so that dx equal to dEk. Because you have this difference in energy at the final quantum state, that happens to be part of a continuum, and En is a discrete state, then dEk is valid but Den is 0 divided by h cross into T by 2. And I'll have to substitute for omega square as well. From this, omega square equal to 4x square by t square. Now we make the substitution of these. So now we make the substitutions here for h prime kn square by h cross square rho of Ek, integral from minus infinity to infinity sine square. Yeah, of course you can make this derivation using the result from harmonic perturbation also, where you will have to replace omega kn by means of omega kn minus omega. So this argument is substituted as a x divided by omega square is there. Omega square is 4x square by t square into dEk. dEk is to be replaced by means of dx, because we have dx equal to dEk by h cross into t by 2, so that dEk equal to 2h cross dx by t. In the next step we will replace dEk by means of this one, 2h cross dx by t. 2h cross dx by t. So h prime kn square by h cross square 4 is there, that is to go with this 4. 4 will be vanishing with this one. So 4 has gone. H prime kn square by h cross square rho, integral from minus infinity to infinity sine square x by x square, t square comes to numerator, and dEk is replaced by means of 2h cross dx by t. One t also will be going, and t is a constant. Integration is over dx, so t is taken out. 2t by h cross h prime kn square rho of Ek, integral from minus infinity to infinity sine square x by x square dx. This result you can prove using gamma function. This value is pi, and it's a standard integral. So we substitute it here. We evaluate the total transition probability to continuum state as p equal to 2 pi by h cross. Pi is taken from this result, 2 pi by h cross into t into h prime kn square rho of Ek. See, look at this. This total transition probability is directly proportional to time. So you make a prolonged exposure. Of course, there will be transition, not between a single, say, one-to-one transition. As this time increases, transition probability also will be increasing in a linear fashion, and is proportional to the square of the matrix element of transition, or square of the magnitude of the matrix element of transition, and further the density of state around the final quantum state, or the continuum state around the final quantum state. So if there are more adjacent quantum states in the continuum, more transition will be there. As time increases, then also the transition will be increasing, and this is proportional to the square of the matrix element of transition. Now the rate of transition, that is the transition per unit time, is equal to p of t divided by t. So time vanishes, we obtain the result as 2 pi by h cross h prime kn square rho of Ek. Thus, we find that the rate of transition to continuum state is dependent on the square of the matrix element of transition and the density of states, and is independent of the time of exposure. And this result is referred to as Fermi's golden rule. It's a very important result as long as some physical problems involving time dependent perturbation is concerned. This is a standard result that I think you might have directly used to discuss the Fermi theory of beta decay, and it is the same result that we will be exploiting to evaluate the scattering cross-section in high energy scattering, or the so-called Born approximation, in the next module. So with that we come to an end for the derivation of the Fermi golden rule. The rule states that the rate of transition to continuum states is directly proportional to the square of the matrix element of transition and the density of states, and is independent of time. This rule is referred to, or this is referred to as the Fermi golden rule. And as long as you people are concerned, this is a very important essay question. Once it is being asked, you begin the story from the first or the evaluation of the probability, amplitude, and probability of transition in time dependent perturbation. Then you just discuss either the case of constant perturbation or harmonic perturbation. Using the result from this analysis, make use of the derivation of Fermi golden rule. And is an examination sure question. Most often it is being asked as an essay question. So prepare this as an essay question, and for the time being I have one assignment for you. Evaluate the transition probability by taking the case of stimulated emission. With this we close for the time being. Now we are left with only one portion in this module, that is the interaction of radiation with matter.